Shark meat processing starts with one unforgiving chemistry problem. Sharks retain urea in their tissue for osmoregulation. And the moment the animal dies, bacteria and enzymes begin converting that urea into ammonia, which is the source of the harsh urine odor people associate with poorly handled shark. A modern shark meat plant is built to win that race by bleeding fast, chilling hard, and moving the carcass through a tightly controlled, cold, sanitary line before the chemistry turns the product uncelled. At receiving, nothing moves until identity and legality are locked in. Sharks are regulated by species, size, season, and landing rules. So the plant records vessel ID, catch area, time, and species declaration, then verifies condition and core temperature. Many facilities add species verification using visual keys, backed by DNA barcoding on random lots. Because mislabeling is a major compliance risk and some species are restricted under CITES or local protections. This is also where food safety starts. Sharks can bioaccumulate mercury and other heavy metals. So premium plants run routine lab panels on higher-risk species and size classes, holding lots until results meet export limits. Temperature control is non-negotiable. Receiving rooms run cold, and fish move through insulated totes with flake ice or slurry ice. Slurry ice is especially effective because it surrounds the surface completely and pulls heat out faster than cube ice, which matters for large-bodied animals where internal heat can linger. The plant tracks time temperature exposure because every hour above target increases ammonia formation and reduces shelf life. If sharks arrive whole, the first step is controlled breakdown designed for speed and cleanliness. Sharks don't have bony skeletons. They have cartilage, which changes cutting mechanics. Operators use long, rigid knives and guided cutting tables to open the belly without puncturing the gut. Because gut puncture spills enzymes and bacteria that accelerate spoilage and create off odors. Viscera are removed immediately. The belly cavity is washed with chilled potable water under controlled pressure to remove blood and residues, without aerosolizing contamination across the line. Bleeding quality is one of the biggest determinants of final taste and color. If the shark wasn't bled effectively on the vessel, the plant may do secondary bleeding by opening major vessels near the gills and flushing with chilled water. The goal is to remove blood that would otherwise oxidize and create dark meat and metallic flavor. Large plants measure this indirectly through color standards at trimming, because blood retention shows up as dark streaks that fail premium grade. Next comes head removal and fin compliance. In regulated operations, fins are documented and handled under strict rules. And many jurisdictions require fins remain naturally attached to the carcass until landing. A compliant plant treats fins as a controlled byproduct, not a separate finning stream, and records weights and counts as part of audit trails. The processing focus, however, is the meat, and the line is designed to maximize fillet yield. While minimizing time out of refrigeration, skinning is where shark processing looks different from most fish plants. Shark skin is thick and abrasive, due to dermal denticles, essentially microscopic tooth-like structures that destroy gloves, belts, and knife edges. Modern facilities use mechanical skinners with toothed feed rollers that grip the skin and peel it away while a fixed blade separates skin from flesh. Roller pressure and blade angle must be tuned to avoid gouging the meat because shark muscle can tear if tension is uneven. The skin, once removed, becomes a byproduct stream. Some markets, it's processed into leather-like materials or collagen, but only if it's handled cleanly and chilled. With the skin off, the plant shifts into filleting. Because cartilage anatomy differs by species, the plant standardizes cuts around the backbone cartilage and fin supports. Filleting is often semi-automated. Workers make primary cuts, and conveyors bring loins to trimming stations where templates and yield targets guide the final shape. Yield control matters because a few % improvement at scale is enormous. And shark carcasses can vary widely in fat content and muscle thickness depending on species and season. One unique mechanical advantage is bone management. There are no pin bones like in many bony fish that make shark attractive for some processed products. But cartilage fragments can still be a hazard if cuts are careless. That's why many plants use X-ray inspection on packed loins and high sensitivity. Metal detection on lines where knives and machinery create potential contamination. Foreign matter controls aren't optional in export plants. They're built into line design with reject gates and recorded verification checks. Now the chemistry problem returns. Removing urea-derived odor. High-tech plants don't mask odor with spices. They reduce the precursors. Loins may go through controlled rinsing and brief soaking steps in chilled water. Sometimes with food-grade acidulants or salt solutions, depending on the product specification and local regulations. The purpose is diffusion and pH management, reduce soluble compounds, and slow bacterial activity. These soak systems are engineered as closed-loop operations with filtration, temperature control, and frequent water changes. Because a poorly managed soak tank becomes a contamination bath that spreads spoilage organisms after rinsing. Water removal is just as important as washing. Excess surface water dilutes packaging atmosphere, increases drip loss, and supports microbial growth. So loins pass over dewatering belts, air knives, or centrifuge-style dewatering systems designed for delicate flesh. Plants measure yield loss here carefully. Too aggressive, and you lose saleable weight. Too gentle, and you ship water instead. Of meat and shortened shelf life, a trimming grading becomes data-driven. Color, texture, and odor are evaluated. But the best plants add objective measurements, pH checks, total volatile basic nitrogen trends, and rapid microbial indicators. Lots that meet premium criteria go to fresh chilled or high-end frozen products, while lower grades may be directed to cooked, smoked, or heavily seasoned formats, where texture is still valuable, but flavor defects are less tolerated. From here, the line splits into product paths. For fresh chilled shark loins, the plant focuses on shelf life engineering. Portions are cut to standard weights with portioning saws or water jet cutters, then immediately packaged in high barrier films. Modified atmosphere packaging replaces oxygen with CO and nitrogen to slow microbial growth and oxidation. Gas ratios are tuned because too much CO can cause package collapse and drip, while too little reduces antimicrobial effect. Seal integrity is verified continuously because a microleak destroys.
Here is the grilled shark, freshly misted for perfect moisture.
It looks delicious. Thank you.
The gas environment and triggers premature spoilage. For frozen products, the core machine is the freezer, and freezing strategy determines texture. Plate freezers, clamp packaged. Loins between cold plates for fast, uniform freezing with minimal dehydration. While blast freezers use high-velocity air for flexibility with mixed products. Rapid freezing reduces ice crystal size, which protects muscle structure and reduces mushiness after thaw. The plant monitors product core temperature at exit because frozen surface is not the same as frozen core. And shipping partially. Frozen fish is a quality failure that shows up as drip loss later. Some plants produce flake-style products common in certain markets where shark meat is cooked and then separated into flakes. Cooking is controlled by time and temperature to set proteins without over-drying. It's often using steam ovens or continuous cookers. After cooking, debulking, and flaking, use paddles and screens to separate clean muscle strands from connective tissue. Because sharks don't have traditional bones, flaking can be efficient. But connective membranes still need removal to avoid chewy defects. The cooked product is then chilled rapidly to prevent microbial growth. Because cooked fish held warm is one of the fastest routes to spoilage. If the plant makes smoked products, it runs the meat through brining, drying, smoking, and cooking. In programmable smokehouses, smokehouses control humidity and airflow as tightly as temperature. Because too dry creates case hardening and yield loss, and too humid prevents smoke, adhesion, and color development. Recipes are logged for every batch because safety and consistency depend on those curves. It's not on operator intuition. Asterisk, throughout all product paths, the cold chain is treated like a mechanical system with alarms. Chillers, freezers, and processing. Rooms are zoned with doors and airflow designed to prevent warm air intrusion. Conveyors are minimized in length to reduce time at ambient exposure. Any accumulation zones are monitored because a stalled belt becomes an unplanned warm hold, can push product out of spec. Waste streams are engineered like a separate factory because shark processing creates heavy, wet byproducts. Heads, skins, fins where legal and documented, viscera, and wastewater loaded with proteins. High-end plants recover value where possible. Skins can feed collagen extraction lines where acid and enzyme processes break down connective tissue into peptides used in food and cosmetics. But only if the input is clean and traceable. Oils from certain species may be separated, but this is tightly regulated and market-dependent. Any human food claim requires additional purification and contaminant testing. Wastewater treatment is critical because fish plants generate high BOD and fats. Screens remove solids first, dissolved air flotation lifts, oils and fine proteins, and biological treatment handles remaining load. Odor control is part of the engineering. Sealed drains, negative pressure in wet rooms. Scrubbers prevent ammonia and fish odors from becoming a neighborhood problem and a worker's safety issue. Sanitation is designed around protein films and biofilms. Clean-in-place systems circulate caustic and sanitizer through piping, tanks, and packers, while open equipment is foamed and rinsed on strict schedules. Knife sterilizers run continuously with hot water baths because knives move between carcasses. And trimming tables in any lapse spreads contamination fast. Verification is measurable lay TP swabs, microbial counts, and environmental monitoring because export plants must prove control, not claim it. Quality control for shark includes tests that aren't as critical for many other fish. Ammonia-related. Indicators and odor checks are routine because urea breakdown is the signature failure mode. Histamine is less of a concern than in certain scombrids, but general microbial spoilage indicators are tracked tightly. Heavy metal testing is taken seriously because top predators can accumulate mercury, and responsible plants manage this through species selection, size limits, and lot testing, rather than hoping results stay low. Even labeling is part of the process. Engineering, species name, catch area, production method, and lot code must match regulatory requirements, and traceability must survive repacking and distribution. Modern plants use ERP systems linking each finished carton back to landing records, processing temperatures, packaging gas checks, metal detector validations, and lab results. That data trail is what keeps a high-volume operation legally defensible and commercially viable. The incredible part of a modern shark meat factory isn't spectacle, it's control. Control of temperature to outrun ammonia formation. Control of cutting and skinning to protect yield against abrasive skin and cartilaginous anatomy. control of washing, dewatering, and packaging to preserve clean flavor, control of testing and traceability to meet strict species and contaminant rules. Without those controls, shark meat is a short-lived, high-risk product. With them, it becomes a standardized protein stream. It's capable of surviving global logistics while meeting modern safety and compliance expectations.